Objective 4, the rational zero theorem. In the previous section, we were given a zero and we used that to find the remaining zeros. Suppose that isn't the case. Suppose we're given a polynomial and we just have to find the zeros. Where would we look? The rational zero theorem gives us a method. Here's a basic statement. You can find this in any pre-calculus book. If P over Q is a zero, and we assume P and Q are integers, P over Q is a rational number of this polynomial. The highest degree term is a coefficient B sub n, and the constant term is B sub 0. The subscripts follow the exponents. If that's the case, then the numerator divides B sub 0. That's what this vertical line means. And the denominator divides B sub n, which is this. Divides or is a factor of. So for instance, 3 divides 15 evenly, and 3 is a factor of 15. So the statement's a little bit terse. When we actually apply it, you'll see the method simplifies it. We're going to go through these 4 examples, applying the rational zero theorem to it. The first example, fx equals 2x cubed minus 11x squared. Forgot the square there, plus 17x minus 6. The first thing we do is list the factors of 6. We grab the last number and list the factors, 1, 2, 3, 6. So we don't care about the minus at this stage. And then we need the factors of 2. The first, do the last coefficient, and then the first coefficient. It's 1, 2. Now, the possible rational zeros, we just need to take numerators from here, denominators from here. So we're going to have 1 over 1, 1 over 2, 2 over 1, 2 over 2, etc., etc. And it can be plus, minus. So we'll do 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, 6 over 1, 6 over 2. And of course, we can eliminate some of these. That's the same as 3. 2 over 2 is the same as 1. And not a bad idea to order these from least to greatest. 1/2 is the smallest, and then we can go to 1. And then we have 3/2. If you're making a list, good idea, cross off the ones you actually do, then 2, then 3, and then 6. So we have 1, 2, 3, 4, 5, 6 times 2, 12 possible rational zeros. We narrowed it down. There's an infinite number of rational zeros, and now, if there are any, we've narrowed it down to 12 possibilities. Next, what we're going to do is just try something. You can start on either end. You can start here and work this way, start here and work this way. Doesn't make one bit of difference. I'm going to divide 1/2 into 2, negative 11, 17, 6. Bring the 2 down. Half of 2 is 1, negative 10. Half of negative 10, negative 5, 12. Half of 12 is negative. That's, I copied a, should be negative 6. Sorry about that. 0. Okay, that's what we want. It divides in evenly. X minus 1/2 is a factor, so x equals 1/2 is a 0. That's the factor theorem. Now, this is reduced to a quadratic. We can factor or use a quadratic formula. I'm going to factor a 2 out. And then we can factor 2x minus 3, x minus 2 equals 0. x equals 3, x equals 2. Can't forget that one. Now, how we answer it all depends on what question was asked. But here's what information we know. Zeros are 1/2, 2, and 3. Now, this is a third-degree polynomial. We should expect 3 zeros. That's what's called the fundamental theorem of algebra. So, as far as the factorization, x minus 1/2, 2, x minus 3, x minus 2. That's f of x, and sometimes this is combined to give you 2x minus 1, x minus 3, x minus 2, if we want integer coefficients. And that's where the 0.5 comes from, and 3 and 2. Okay, let's take a look at the next one. Okay, that's a 50 there. Make no mistake, it's not a 6. Now we want the factors of 50, and you can do 1, 2, 3 doesn't, 4 doesn't, 5 does, and 6, 7, 8, 9, 10. Okay, and then 25 and 50. Now, can you compare these up? 5 times 10, 2 times 25, 1 times 50. Factors of 1 are just 1. So possible rational zeros are plus or minus 1, 2, 5, 10, 25, 50. So we just happen to have integers. You could try 1. Actually, 1, you could see if it's a 0 very easily. Just add up 1 minus 2 minus 25 plus 50. That doesn't add up to 0, so you can forget 1. How about 2? Let's try 2. 1, negative 2, negative 25, 50. 1 minus 2, 0. 0 minus 25 minus 50. 0, we're in business. And so we get plus or minus 5. And if you want to list out all the zeros, you have to put x equals 2 here. There's the zeros, and you can finish up with a factorization. One quick note, this polynomial factors by grouping. Not all of them do, some do. You can factor x squared out, minus 25, x minus 2. Factor x minus 2 out. Leaves x squared minus 25. And there you have it. Okay, zeros are 2, negative 5, and 5. Same result. So let's have a look at this one right here. Okay, you notice we can factor x out first. And then apply the rational zero theorem to this. Well, we've already done that. That's problem number 2. So we get x equals 0 from here. And then this is from the previous problem, x equals 2, x equals plus or minus 5. You apply rational zero theorem here. You can forget that, but don't forget that 0 that came from the beginning. So, last problem. We have a 4th degree polynomial, and it's worth discussing, and we want the factors of 6, 1, 2, 3, 6. Since the leading coefficient is 1, we can just skip the possible rational zeros, plus or minus 1, 2, 3, 6. Now let's try 1. You can actually do 1 mentally. 17 minus 17 is 0. 6 and 1 minus 7 is 0. 1 works. Let's try 1. 1, negative 7, 17, negative 17, 6. We know the outcome. You get 1, 1, negative 6, 11, 11, negative 6, 0. Now this is a 3rd degree polynomial. 4th degree, divide out 1 factor. 3rd degree, we can't just factor that like a quadratic. So circle that. There's no reason why we can't try 1 again. You can have repeated zeros. Bring the 1 down. 1, negative 5, 6, 6, 0. We're in business. And now here we have x squared minus 5x plus 6 equals 0. X minus 2, x minus 3. X equals 2, x equals 3. Now if we want all the zeros, you really have x equals 1, x equals 1, x equals 2, x equals 3. And this can be rewritten as x minus 1 squared, x minus 2, x minus 3. And this is equal to f of x. Very easy to graph. We have zeros at 1, 2, and 3. It goes right through at 2 and 3, and it goes parabolic at x equals 1. This here is sometimes simplified. Let me erase this. We're almost done here. Sometimes we say x equals 1 multiplicity 2. If we have repeated zeros, and you can see if we had 5x equals 1 equal ones, we'd want to write just x equals 1 multiplicity 5. It doesn't necessarily affect the solutions, but it affects the graph, obviously. If this is a 1, 2, or a 3, it gives you different looking graphs. So that's all for the rational zero theorem.